So, last week we started a new topic called center of gravity and centroid. I mentioned it's going to be an interesting topic because it's not as intuitive as everything else we've been doing so far. And that's why we decided to dedicate 2 whole weeks to them. So last week, if you attended the lectures or if you saw the videos from the lectures, then you know that we went through several examples from the book, as well as one of the homework problems. And then there's additional videos from additional examples that we did during the review session, which I will upload probably sometime this week. So we're going to have different resources to look for. Now, you're not really required to watch anything beyond the 2 videos for last week, but I would strongly recommend that you do watch them because we're solving different examples, different problems. And the good thing about these examples is that they're all solved slightly differently, right? So the more we solve, the more we can get used to actually solving and finding centroids, as well as centers of gravity and centers of mass. Now, we've been focusing on centroids these days, so I want to continue that conversation on centroid. And I want to start with example 9.6 from the book. Last week, everything we did was one-dimensional, with the exception of perhaps the last 2 or 3 problems that I haven't uploaded yet. So this week, I want to focus on 2- and 3-dimensional shapes. Okay? So let's say we're given half of an ellipse, right? Half of an ellipse with a large radius of 2, a small radius of 1. And we want to find the coordinates to the centroid, that's x bar and y bar, of this ellipse. Now, we mentioned that when we're dealing with 2-dimensional areas, we always want to make sure that we are aware of what the limits of our area are. So in this case, this shape, right, this half of an ellipse, is bounded by 2 curves, right? We have the curve of the ellipse, which is x squared plus y squared over 4 equals 1. And then we're also bounded by this line. What's the equation of this line that goes through the x-axis? Y equals 0, right? So our shape is bounded by these 2 curves. And we want to find the centroid. Now, based on the symmetry of this shape, what do you think we can deduce about the centroid just by looking at the shape? Is there anything we know about where the centroid will be located? Yeah?
Center of mass is going to be along the y-axis.
Exactly, right? We know the centroid is going to be along the y-axis. Because notice that wherever your centroid is, you know that you're going to have the same amount of ellipse to the right of the y-axis as you do to the left of the y-axis. So we know that at least the x-coordinate, x bar, for the centroid will be 0. And let's see if that's right, okay? But at least we have an idea of where we should be heading to. Now, we can't really say the same thing about the y-coordinates, right? We can't say that the centroid has to be here. It cannot be here. So we will have to do a little bit of working out in order to figure out where our y-coordinate of the centroid is. So let's start. I mentioned that I don't like these recipe-style examples where we do step by step, but I make an exception for centroids because really the steps for determining a centroid are pretty much the same regardless. So I already mentioned last week that you want to start this problem by setting a differential element now in 1 dimension, that differential element will have a differential length dl. But in 2 dimensions, that differential element would have what type of dimensions? dA, right? So we're going to set a differential element dA that is located at some arbitrary point, which I'm going to call xy. Okay? And this will be an arbitrary point in my curve, because we know that to find centroids, we integrate. And if we integrate, mathematically, we're finding the area under a curve, right? And what is the curve? Well, the curve is x squared plus y squared over 4 equals 1. So we want to make sure that our differential element dA can be located with respect to an arbitrary point xy that lies on this curve. So that's what I'll do. I'm going to locate my differential element at some point, and I'm going to call this point x, y. And my differential element, you can do a horizontal element, you can do a vertical element. I'm going to choose to do a vertical element today. Regardless of what type of element you do, you're going to be able to solve it and you will still get the same answer. However, sometimes your integrals will be easier if you choose one orientation over another. So I have my differential element. It's a tiny, tiny, tiny element. In this case, a thin, thin, thin element with an area so small that we can only quantify it as dA. Okay? After we set our differential element at some arbitrary point, the next step is to find the coordinates of the centroid of that differential element. And we mentioned that we're going to call those coordinates x squiggly and y squiggly. So we're going to find the coordinates of the centroid of that element. And remember that those coordinates have to be found in terms of this coordinate point xy. In other words, x squiggly and y squiggly have to be functions of x and y. There's another thing we need to look into, right? Not only do x squiggly and y squiggly have to be functions of x and y, but we'll see that when we try to solve this problem, we will actually want to express these not just as functions of x and y, but also as functions of whatever differential length you chose. But we'll get to that, okay? So for now, let's take it step by step. Let's find x squiggly and y squiggly. Now this is a differential element, right? Which, if we were to zoom in as much as we can, we would essentially see a rectangle, right? So where do you think is the centroid of this differential element? The centroid of that little rectangle. Where's the centroid of a rectangle? At the center, right? So I know that for this tiny element dA, the really, really small element, the centroid of this tiny element, just for that element, is going to be located at the center of the rectangle. And I'm going to call this coordinate x squiggly, y squiggly. Now my question is, how does the coordinate point x squiggly, y squiggly relate to the coordinate point xy? So we'll see that. In the x direction, I get that my x coordinate, x squiggly, is equal to the distance, right? The horizontal distance normal to the y-axis. Let me just draw this a little bit straighter. Did I make it straighter? I think now everything is rotated. But anyway, the horizontal distance from this y-axis, okay? In other words, my x squiggly is this horizontal distance, right? That's the x coordinate. But now we want to see how this x squiggly relates to my x coordinate. And notice that here my x coordinate is also a horizontal distance. So what do you think is the difference or the similarity between these two distances? They're equal. So can I say that x squiggly equals x? Yes, good. So I found x squiggly, the centroid of that rectangle, as a function of my coordinate point x that lies on that curve. Now I can do the same for the y direction. Here, my y coordinate, remember, is the distance from the x-axis, which I'm going to call y squiggly. And then I have this y coordinate, which is this distance from the x-axis. Are those two distances equal? No? What's the relationship between those two distances?
Y squiggly is 1/2 y.
Exactly. Y squiggly is 1/2 of y. So we found x squiggly and y squiggly, both of these as functions of x and y. Third step is to express our differential area, and we call the differential area dA as a function of either dx or dy. And the question is, how do we know which one we're going to use? We know by looking at our differential element. So I'm going to draw my differential element here just so that we can have it as a reference, right? I have a differential rectangle. In terms of x and y, what is this height of my differential element?
The height is y.
Y, right? Yep. And what do you think is the width of this element? Dx. Good. So now, when I try to find my area dA, what is the area of this rectangle? Y dx, right? Good. Now, y, as you can see in this curve, is actually related to x. So we can't really treat it as if it were a constant, right? As x changes, y changes. Therefore, because we are using a differentially small distance dx, we want to express our dA always in terms of dx or x. In other words, here my dA is equal to y dx, but y needs to be expressed as a function of x. Now remember, y and x are points along this curve. So is there any way we can relate y to x using this curve?
With the formula.
With the formula for the curve, right? We have an equation here, x squared plus y squared over 4 equals 1. So if I were to find a relationship between y and x, I get that y equals what?
Square root of 1 minus x. The square root of 4 minus x, 4x squared.
All right, let's think about this. All right. Oh, I see what I did wrong here. I wrote the ellipsoid equation incorrectly. It should be x squared over 4 plus y squared over 1. Right? X squared over the square of the x coordinate, y squared over the square. Yeah, there we go. X squared over 4 plus y squared equals 1. There we go. So now what is y?
The square root of x squared over 4.
There we go. Close, close.
Plus,
There we go.
minus.
Very close, right? Y is the square root of 1 minus x squared over 4. Just move x squared over 4 to your side, and you get your y coordinate. So I can say that dA, which is equal to y dx, is actually just equal to y, which is square root of 1 minus x squared over 4 times dx. I mentioned earlier that when you draw your differential element, by drawing it, you will already know if you're going to be using dx or dy, right? Because when I draw this element here, I know that the tiny distance is going to be dx. Because of that, I know that I will be integrating with respect to x. And if I'm integrating with respect to x, I know that I can express these centroid equations always in terms of x. So I get that x squiggly equals x. I don't have to do anything there. It's already x. But I get that y squiggly equals 1/2 y. However, I know that I'm not going to integrate over y, right? I want to express it as a function of x. So 1/2 y is actually 1/2 times what? If I want to express this as a function of x.
Square root of 1 minus x squared.
There we go. So I've completed what's essentially the hardest steps in this problem. Now, the final step is to integrate. So we solve for x bar and y bar. We know that x bar equals the integral of x squiggly dA over the integral of dA. In this case, we know that the integral of x squiggly dA should be the integral of x squiggly, where x squiggly simply equals x, so I'll just write it here, times dA, where dA equals square root of 1 minus x squared over 4 dx. Now, because we are integrating along the x direction, what are my limits of integration here? What's the domain of x here? -2 to 2. That's correct. And the denominator we have from -2 to 2, the integral of -1 minus, or the integral of square root of 1 minus x squared over 4 times dx. Based on that figure, what do you think this has to equal? 0, right? So let's see if that's true. Let's integrate the term on the numerator. What is the integral of x times square root of 1 minus x squared over 4? That one should not be that complicated, right? What do you think?
You can remove the constant. No.
There is no constant here,
Yeah.
right? But it's okay. Remember one thing. The derivative, right, of square root of something with x should be equal to this elevated to the exponent -1 times the derivative of x. So in this case, it may not seem too, what do you call it? It may not seem too straightforward, but in this case, this integral actually isn't that complicated. This one, however, I'll leave it to you to figure out. But the numerator integral is actually, I'm just going to write it down so I don't make a mistake here, but it should be 1/6 4 minus x squared 1/2 plus 1, which is just 3/2. And of course, all this is evaluated from -2 to 2. This one's a different monster altogether. So I'm not going to try to even pretend that I know how to find this integral. I'll just copy it here for you, courtesy of Wolfram Alpha. So 1/4 square root of 4 minus x squared plus inverse sine of x over 2. All this evaluated from -2 to 2. Okay, we know that this has to be 0. So does this equal 0? What do you think?
Yeah.
Yeah, right? We have 2 elevated to the power of 2, that's 4. 4 minus 4 equals 0, all this goes to 0. Minus, then we evaluate at -2. So -2 to the power of 2 is also 4. 4 minus 4 is 0, so all of this on the numerator goes to 0. So we get that the x coordinate of the centroid is 0, just as we predicted. Good. Yeah?
But that doesn't necessarily mean that our numerator is going to equal our denominator, correct?
That doesn't know. No.
Okay.
Only the numerator equals 0, the denominator equals something else.
So you really don't even have to solve the denominator.
No, we could have just left this as integral dA, right? Because we would have gotten 0 over the entire integral, not even have to solve it. Until we get to the y-coordinate of the centroid. So, y-coordinate of the centroid equals integral of y squiggly dA over integral dA, as we've already seen. So we get integral y squiggly, as you can see here, y squiggly equals 1/2 square root 1 minus x squared over 4. So 1/2 square root 1 minus x squared over 4 times dA. And dA, as we found in step number 3, equals square root 1 minus x squared over 4. This looks like it's going to be a hard integral, but it actually isn't, and you'll see why in just a second. Evaluate from -2 to 2. On the denominator, we have integral dA, which we already have here. So this is 1 minus x squared over 4 dx. Oh, what is this times this? Square root of 1 minus x squared over 4 times square root of 1 minus x squared over 4. Exactly, right? So we got the integral from -2 to 2 of 1/2 times 1 minus x squared over 4 dx. So this actually becomes an easier integral to solve. So let's integrate this top part. I think this should be easier for all of us. Let's see, the integral here would be 1/2 times x minus 1 over 12 x cubed evaluated from -2 to 2. Can somebody confirm that number? Can just let me know if this integral is correct. Is this integral correct?
Yeah.
Yes. Good. All right, so we evaluate, right? So we get x equals 2, right? And solve, and then x equals -2 and solve, okay? Graham, use your calculator.
Forgot one.
It's okay, you have a, is that a tablet?
It is.
I'm pretty sure there's a calculator in there somewhere.
Maybe.
Maybe. Let's see, we have 2 minus 1/2, 2 to the power of 3. How much is 2 to the power of 3? That's 8, right? So minus 8 over 12. So 2 minus 8 over 12, all that multiplied by 1/2. This will always be 0, and this will be inverse sine of 1. What's the inverse sine of 1?
0? 1?
What angle gives a sine?
Arc sine of 1.
There we go.
90.
90, right? Good. We call it arc sine when we're just using the calculator, because inverse sine is too long, okay? So 90 degrees in radians, that's how much?
Pi.
Pi over 2, right? There we go. So in the denominator, at least, we have pi over 2 minus, and then what's the inverse sine of -1? What angle gives a sine of -1?
3 pi.
Exactly. Or negative pi over 2, right? Good. So minus negative pi over 2, that's plus pi over 2, so we're going to have pi in the denominator. What about the numerator? Four thirds? Is that what you said? Can anybody vouch for that number? Awesome. So 4 thirds, pi over 2 plus pi over 2 is simply pi. So 4 over 3 pi. Okay? If we plug that into our calculator, 4 over 3 pi should be 0.424. In this case, we were given units, so I can write 0.424 feet. But remember that when we're dealing with centroids, I typically try to stay away from units because we want to focus on the theory first. Make sure we understand that before we start applying it. So we have solved a 2-dimensional centroid problem. And we actually did it faster than what we were doing last week, so it's actually not bad. However, I do need to make sure that you understand all this. So I'm going to find the most awkward and uncomfortable way to ensure that you understand this topic. Jared, can you explain to me what we did in step number 1? Set a differential element dA located at xy.
What you did is you had your given figure,
Mm-hmm.
and then you picked an arbitrary point,
Okay.
and from that arbitrary point, which you labeled xy,
Uh-huh.
we found the height, which we called y,
Okay.
and the width of that arbitrary rectangle that we drew, aka dA.
Good. So could we have solved this problem if our element would have been horizontal?
Absolutely.
Yeah, we could have, right? The integrals would look different, but the final answer would still be the same. Sophia, what do I mean when I say find x squiggly, y squiggly in terms of x and y?
So x squiggly, y squiggly is the midpoint of the square that we created,
Uh-huh, rectangle?
of the rectangle we created.
Uh-huh.
So we want to find what x squiggly and y squiggly is in terms of the actual coordinates that we have.
Okay, thank you. Kevin, why is x squiggly equal to x? feel like this may be bringing bad memories of the oral exam now that I think about it. But why is x squiggly equal to x?
Because the coordinate of our element
Uh-huh.
really is the same as
Yeah, you're good.
between x and the element.
Yeah, right. We have the same distance at both. Daniel, you know why y squiggly isn't equal to y, right? Because we only have half of the distance of y in the total distance. So then how do I get this expression, dA equals square root of 1 minus x squared over 4 dx?
Is it because our ellipsoid equation and plug it in?
Yes, but we missed one step, right? We know that dA is the area of this rectangle, right? And the area of the rectangle is length times width, right? So y dx. And then we go to what you said, right? We use the ellipsoid equation and just solve for, in this case, solve for y and then plug it in as a function of x, right? Luis, how do I get that this integral in the denominator equals this beast? I'm kidding. I'm not going to ask you to solve that. All right, so we understand, right, how to solve this problem. Let's make it a little bit more complicated, okay? So we did a lot of 1D last week. We did a couple of 2D problems last week. But we haven't done anything in 3 dimensions. So I would like for us to start with a 3-dimensional problem and hopefully finish, right? I have a question. The equation that we use for centroid, let's say in the x direction, was this one, right? That's what we just used. How would that equation change if we're using 3 dimensions?
Instead of it being the derivative of the area, would it just be the volume?
Exactly, right? Instead of dA, we would have dV, because in 3 dimensions, we are dealing with volume, whereas in 2 dimensions, we were dealing with area. That is absolutely right. You'll see that other than that very small change, the rest of the problem is actually going to be exactly the same. So even though we're throwing in the word 3 dimensions there to make it sound like we're actually doing something more complicated, it's actually not. It's actually pretty much the same. Now, don't rely on my artistic abilities. Go to your book, example 9.7, in order to actually see what this figure looks like. But I have, let's say I have my Cartesian coordinate system, x, y, and z. And I would like to draw this shape. What does the book call this shape? A parallel something, right? It's essentially not a cone. Kind of looks something like this.
Looks like an icon.
Right? Something like that. So it's a 3-dimensional shape, and it expands this way along the y-axis. In other words, the y-axis passes through the center of that shape. Okay? So it expands on the y-axis. This shape, if you were to take a cross-section, you will always see a parabola in this shape. Okay? Which means that you can define, if y equals 0, you can say that z squared equals 100y here. If x equals 0. And then if y equals 0, you can say that along this side, z squared equals 100x. It's simply always going to be a parabolic shape. And I'm going to say, in order to find the end of this cone, it ends when the radius of this sphere is 100. Okay? So this, if you were to take a cross-section in this direction, you will see a parabola. If you were to take a cross-section in this direction, you would see a circle. Okay? That's the shape that we have. It's not a cone. What's it called? A paraboloid, right? Okay, good. A paraboloid. Whew. I'm assuming that would be paraboloide in Spanish, but who knows? Yes.
Can you describe the shapes of the cross sections again?
Yeah. If you were to cut it in this direction, you would see a circle, right? So if you're standing along the y-axis and looking towards the y-axis, you see a circle. But if you look at it from the side, like if you stand on the x-axis and you look at it from the side, you see a parabola. Okay? If these were straight lines, it would be a cone, essentially. But it's not straight. Okay? Okay, so we would like to find the coordinates to the centroid. X bar, Y bar, Z bar. Based on the symmetry of this shape, what do you think will be the x coordinate of the centroid? Remember, x coordinate in this direction. So in this direction, parting from the origin, where do you think the centroid will lie with respect to x?
On the y-axis.
On the y-axis, which is x equals
0.
0. Good. So just from looking at it, we know that x bar should be equal to 0. But remember, even though we know, we can still solve it the way we would have solved it. So we're going to solve it. I just want to make sure that we know what answer to expect. What about the z coordinate? Again, we mentioned that the centroid should lie along the y-axis because the y-axis actually passes through the center of every cross section here, right? So what do you think is the z coordinate for the centroid? If it's on the y-axis?
It should be 0.
0, right? So we know that z bar equals 0 because the centroid will be somewhere along this y-axis. So in order for a point to be on the y-axis, its x and z coordinates both need to be 0. Otherwise, it wouldn't be on the y-axis. It would be away from the y-axis. Okay? So we know, or we expect, I don't want to say we know, we expect x bar and z bar to be 0. So let's see if that's actually the case. When we solve a problem like this, we already mentioned that the first step would be to set a differential element. Now, in one dimension, our element had an infinitesimally small length, dl. In 2 dimensions, our element had an infinitesimally small area, dA. In 3 dimensions, what do you think our element needs to have? An infinitesimally small what? Volume, right? So we're going to call that dV. And it's going to be located, normally we locate it at an arbitrary location x and y. In this case, we're going to locate it at an arbitrary location x, y, z. Good. So when we're looking at areas, our element was typically a rectangle. In this case, you want your element, right, to have a volume that somehow conforms to the shape of this thing, this paraboloid. So what we're going to do is, you can always set your element to be horizontal, to be vertical, but you always want to pick what's easiest for you. So I think instead of dealing with a horizontal element so that we need to solve for the area of a parabola, I would like to do an element that has its center at the y-axis. In other words, I'm going to grab a tiny slice, right, of this paraboloid. And that slice, that tiny slice, is going to look like this. There's like a tiny little circular plate along this paraboloid, right? Imagine this to be circular. So a little circular plate with a tiny, tiny, tiny volume dV. So here's my element, tiny volume dV. Just out of reference, because I'm sure you may be wondering, the reason I write volume with this is because in fluids class and dynamics class, you want to distinguish your volume from your velocity. So I kind of got the habit of writing volume with a little mark. Okay? You don't have to do it that way. But when you do get to fluids, which I can already see that some of you are taking it with me based on the registration, we will be using that line for dV. Okay? So we have our element. Tiny, tiny element. When it was an area, typically it was a very thin element, right? It had some finite dimension, and then the other dimension was really thin. When it's a volume, it's going to be a very flat element. It's going to have 2 finite dimensions, and then the third dimension is going to be very, very, very small. And that's what we have here. We're going to have a flat element with 2 finite dimensions, right, which is this circular area shape. But then the thickness of that area will be very, very, very small. Okay? So we have set our differential element dV at coordinates x, y, and z. What was this? What was the next step? What should we do after setting our differential elements?
Find the coordinates of the centroid of the differential element.
Okay, so we want to find the coordinates of the centroid of this volume, right? In other words, x squiggly, y squiggly, and what else?
Z squiggly.
Z squiggly. I mentioned last week, I'm going to say it again. Nobody else calls it squiggly, so don't repeat that outside the classroom, because people are going to look at you and think, what is this guy talking about, okay? So we want to find the coordinates to the centroid in terms, right, of your x, y, and z coordinates. Now, you may think that because we're looking at 3 dimensions, this problem is actually more complicated, but it's actually not. Where is the centroid of this tiny flat plate? Remember, the flat plate has a circular cross section. In the middle, right? Good. So we know the centroid, x squiggly, y squiggly, z squiggly. Doesn't matter where the plate is, it's always going to be in the middle of that plate. So what does that tell me? What do we know about x squiggly right now? What is x squiggly equal to? Remember, the centroid is along the y-axis, right? So what does x squiggly equal?
0.
Okay. Let's look at y squiggly. Here, y squiggly is at some coordinate, right? And how is that y squiggly coordinate related to your arbitrary point x, y, z? By the way, I should have mentioned the arbitrary point, remember, is going to be a point along this area. Before it was a point along the curve that we're going to integrate. Now it's going to be a point along the area, the surface area that we're going to integrate. So you can say, for example, that your x, y, z is here. So in terms of x, y, z, right? What is y squiggly equal to?
Y.
Just y, right? And what do we know about z squiggly here? 0. And notice that it doesn't matter where you draw your element, the centroid will always be in the y-axis, which means that x squiggly and z squiggly will always be 0. Okay? Because the centroid is always the center of the circle for this circular plate element. Good. Any questions up to this point? Is that just how your face looks? Does you look like you're mad or doubtful?
See, I got bad eyes.
Okay, I see. How you were mad at me? I was like, what did I do? Did I not use the correct expression? Okay. Woo. All right, step number 3. Finally, not finally. Step number 3. We want to express our differentially small volume, which I'm going to call dV, as a function of dx or dy or dz. You look at this element has 2 finite dimensions and 1 infinitesimally small dimension. What is that 1 infinitesimally small dimension? dy. So you're going to want to express your differentially small volume dV as a function of dy. So I look at my differentially small element. I'm going to draw it again here. That's my differentially small element. It's essentially like a very tiny, very thin circular plate. What is the area of this circular plate? What is the volume of the circular plate? Which will be the area times the length times the width. What do you think? What's the area of a circle?
Pi squared.
Okay, so what's the radius of this element in terms of x, y, z?
With E.
Say it?
The Z.
Z, yeah. Now, we know that because this is a circle, z should be equal to x. Doesn't matter. But here, our arbitrary point, right, dictates that our radius is z. Because since our point is up here, x equals to 0 up here. If our arbitrary point would have been here, I couldn't really draw it well, but if our arbitrary point would have been here, then z would have been 0, x would have been our element. But that really depends on where you place your arbitrary point. So in this case, we know that the area of a circle is pi r squared. And then how do you get the volume of a cylinder, which is essentially what this is?
Just times it by the thickness.
Exactly, right? You multiply it by that distance, that thickness. So in this case, my volume dV is going to be equal to pi r squared. And we said that the radius was simply the coordinate to my point z. So pi z squared multiplied by what? By the thickness. But what's the thickness?
dy.
There we go, dy. Good. Because our differential element is in the y direction, our differential dimension is dy, we want to make sure that our squigglies are also in terms of y. Nothing, y, nothing. We're good. Right? If we would have had an x or a z here, then we want to change those to y. Okay? And finally, now we get to find that differential element. Okay? And before I continue, we do have a z value here, and this is y. So we want to make sure that everything's in terms of y. Is there any way we can relate z to y for the curve?
Z squared.
Exactly, right? We get that z squared equals 100y, right? So I get z squared equals 100y. And what then is the final step?
Integrate.
All right, can you say it like you're actually excited to do it?
Integrate.
There we go. The final step is to integrate. And then we solve this problem. We know that the x-coordinate of the centroid, let me use a different color. We know that the x-coordinate of the centroid is the integral of x squiggly dv over the integral of dv. What was x squiggly equal to? What? So this is equal to? Good. We know that the z-coordinate, I'm just going to skip to z's, is the integral of z squiggly dv over integral dv. What was z squiggly equal to?
0.
All right, so all this goes to 0. And we know that the y-coordinate is equal to the integral of y squiggly dv over the integral dv. In this case, we get that y squiggly equals y. So I'll write it down, y. And we get that dv equals 100 times pi times y times dy. So 100 times pi times y times dy. Denominator, I have integral dv, which equals 100 times pi times y times dy. And we want our limits of integration. From where to where are we evaluating the y-axis or the y-coordinates?
0 to 100.
From 0 to 100, right? Because in order for z squared to be, or in order for z to be 100, y has to be 100, right? Because z squared equals 100y. So if z squared is 100 squared, then y has to be 100. So from 0 to 100. Good. This is actually a pretty easy integral. Let's take out all the constants. 100 out, pi out. I get integral from 0 to 100. Y times y equals y squared dy. 100 out, pi out. Oh, look at that. Convenient. Integral from 0 to 100, y dy. What does this give me? Now, 100 cubed, right, over 100 squared. Something's wrong here.
Okay.
Yeah. No, it's right. 100 cubed over 100 squared. Go ahead.
I have a question
Yeah.
about the limits of integration.
Yeah.
I said 100 kind of softly because it seems like that limit is on the z-axis. It's in terms of z.
Well, this is a z coordinate. That's true. So this is 100. That's not the reason why the answer is 100. So this is 100. but you know that z and y are related by the equation z squared equals 100y. So on the z-axis, right, you know that this would go from 0 to 100. On the y-axis, this goes, you can tell it's 0, right? But then why does it go to 100? Because at this point in the y-axis, z equals to 100, right? So this is 100 squared equals 100y. Y equals 100 squared over 100, just 100. Okay? So we use the equation to solve for the limit. Okay?
Thank you.
No problem. All right, so what do we get? 100 cubed over 100 squared, that's 100. So 2 over 3 times 100, that should be 66.7, right? We did it. We solved for the centroid of a 3, not 1, not 2, but 3-dimensional object. Any questions? No? You know I have to do it, right? So, Tuong, can you explain to me what we did in step number 1?
We try to find the differential, the differential element, which is this small part of the.
You're good, you're good. Yeah, we found a differential element, which is just a tiny, I'm going to call it slice, right? A tiny slice, right, of our entire body, right? That element was located at an arbitrary coordinate x, y, z, right? And that coordinate was found over the top curve, okay? You could have picked whatever curve you wanted for your coordinate, but the important thing is that you know that x, y, z has to lie somewhere on the surface of this shape because we're going to integrate over the volume of the shape. So if we're going to integrate over the volume of the shape, we need to know what the surface area of the shape is, okay? We found the coordinates to the centroid of that element. Noah, why is x squiggly and y squiggly here equals 0 for that element?
When you examine where it's located, on the x-axis, the point of rotation is all about y. And if we're starting from that origin, a circle moving along just the y-axis will be staying at 0 in the z and x.
That's right. So we know that our centroid is at the y-axis, and the y-axis is simply a line defined by x equals 0, z equals 0, right? So x squiggly has to equal 0, z squiggly has to equal 0. We express dv as a function of dy. I don't think there's too much to do here, right? The area of a circle is pi r squared. In this case, my radius is my z coordinate. And then the thickness of the cylinder is simply dy. Not too much stuff there. And then we integrated, and we ended up with pretty easy integrals. So any questions with the integrals? No? Okay, yeah. So that is how we solve a 3-dimensional body, centroid. Finally, I'd like to go over another 3-dimensional problem. However, we've focused all our attention on centroids. I would like to look at the center of mass because I want us to see the difference, right, between centroid, center of mass, center of gravity. So in this case, I would like to focus on center of mass. And we'll do so by working through example number 9.8. All right, again, do not depend on my artistic abilities. I'll try my best to draw something clearly, but if you have any questions, feel free to ask. Whew. So what we are going to have here is a cylinder, okay? So the cylinder with its base on the xy plane. I gotta plan this out, okay? I can't just draw randomly. So we have this cylinder with this base on the xy plane. Oh God. My goodness. We're getting there. Hang on. This signifies that these are the edges on the back, okay? All right. So we have a cylinder on the xy plane. What if I were to ask you to find the centroid of the cylinder? First off, I don't think you would need to solve any equations here. If I were to give you some general dimensions, I'll say that the cylinder has a length of 1 meter, and let's say it has a radius of 0.5 meter. So my radius is 0.5 meter from here to here. If I were to ask you to give me the coordinates of the centroid of the cylinder, what is the x-coordinate of the centroid of the cylinder? 0. Good. What's the y-coordinate of the center of the cylinder? 0. What's the z-coordinate of the center of the cylinder? 0.5. Good. So if I ask you to give me the centroid, you can give me the centroid with no issues here. You can draw your equations again and land at the same answer, 0, 0, and 0.5. But now let's say that this cylinder is not a homogeneous material. In other words, it does not have constant density. Okay? So let's say that the density of this cylinder actually varies with respect to z. Okay, so my density will be 200 times z, and the units will be kilograms per cubic meters. Okay? What does this mean? If my density varies with respect to z, at z equals 0, right, at the origin, what's the apparent density of this object at z equals 0? 0, right? Now, of course, this is a bit of an exaggeration, right? But what this means is that basically my density will increase with my increase in elevation. So at the bottom, the density is really, really, really small, right? So small that it actually limits towards 0, right? But at the top, what do you think is the density at the top? 200. Okay, so it increases linearly from 0 to 200, okay? So you know where the centroid is. The centroid is at 0, 0, 0.5, right, at those coordinates. But what if I want to find the center of mass? In other words, I don't want the coordinates to the centroid. I would like for the coordinates to the center of mass. Does anybody remember what equation we used to find the coordinates of the center of mass? When it was centroids, we integrated over lengths, areas, or volumes, right? What about when it's center of mass? What are we integrating over? Exactly. And what is m? Mass. The center of mass, we integrate over mass. So my x-coordinate will be equal to integral of x squared dm. My y-coordinate over integral dm. My y-coordinate will be equal to integral y squiggly dm over integral dm. My z-coordinate will be equal to integral z squiggly dm over dm. That's the only thing that changes. Everything else remains the same. But my center of mass, right, requires me to integrate over a mass and not a volume. And you'll see that when we're integrating over mass, we actually are able to apply this density, this varying density. Now, why is that? How do we define density? What is density?
Mass per unit of volume.
Mass per unit volume, right? Now, when we're thinking in terms of calculus, we think of differentially small elements. So if you were to pick a tiny, smallest possible element on this body, then the density, we can say that the element is so small that the density at that one point is a constant, right? Density cannot vary through a point. It can vary if you move to a different length, to a different area, but at that point, the density is constant. At that point, the element is so small that its mass is dm. And what do you think is the volume of that element if it's so small? dv. Now, why am I doing this? We have density equals dm over dv. Or we can say that dm equals what?
Density times dV.
Exactly. So even though I'm integrating over a mass, which it is what I'm doing, this is actually the same as me saying integral x squiggly, and instead of dm, I can say rho dv. And at this point, with the addition of this extra term, is our equation any different from what we've already done? It's pretty much the same equation, right? So let's solve it and let's see if the steps can remain the same or if there's something that we may need to add or remove. First off, density really only changes in the z direction, which means that, what do you think that means for the x and y coordinates of the center of mass? They're still 0, right? Okay, so we have some values that we can expect, and that's good. So, because we then have something to look forward to, right? So, let's start by setting a differential. Now, before we set, we used to say that we set a differential element dv. In this case, we're going to set a differential element of mass dm. But we already know that dm is equal to rho dv. So we're going to set a differential element with mass dm but we know that dm is actually equal to rho dv. So differential element with density rho and volume dv. And we are going to locate that element at an arbitrary point. Okay, so we're going to set that differential element and we're going to locate it at some point x, y, z. You can choose a point wherever you want here. You'll see that it actually doesn't change anything, right? Your integral will still be the same regardless of where you choose your point because of how this problem is set up. So I'm going to set my differential element. What do you think it's better for us? Should we set an element maybe in this direction where the cross section is a rectangle? What do you think we should do?
No.
So what else should we do instead?
Circular.
Yeah.
Show it up.
Okay, so maybe an element cutting right through the xy plane or in the xy plane direction so that our element is actually a circular plate, right? So we're going to do that. We have our differential element. And this is a flat plate so small that its volume can only be quantified by dV. We know that we're actually looking at the mass of the element, dm, but we know that dm is simply rho dV. Okay? So we have set our differential element. And let's give it, right, let's give its coordinate some arbitrary point. So I'm going to pick an arbitrary point here. I'm just going to call it x, y, z. After I set my differential element, I will have to find the coordinates to my centroid, to the center of mass of that element. So I'm still going to call them x squiggly, y squiggly, z squiggly. But these are coordinates to the center of mass. Now, if you look at this element, and here's why it's important to have set it up this way. Because my element is a horizontal circular plate, does the center of mass vary in the x and y directions for this element? It doesn't, right? And that's good, because if we would have actually set our element to be a vertical rectangle, my center of mass would actually not be in the middle of that element. I have to still try to find out some way of solving it, okay? So I want to find x squiggly, y squiggly, z squiggly. Let's start with x squiggly. The coordinate to the center of mass of this element. What's the coordinate to the center of mass of my element?
0, 0.
Okay. What's the y coordinate to the center of mass of my element?
0.
What's the z coordinate to the center of mass of my element? Z, right? Because the element is located at an arbitrary point x, y, z, which means that this distance from here to here is the same as this distance from here to here, right? So d squiggly equals z. So we want to express our differential element's mass. So we're going to express dm as a function of what? You have your differential element. Notice that for your differential element, we have two finite dimensions and one infinitely small dimension. What's that one infinitely small dimension? dz, right? Okay. So we want to express our differential mass dm as a function of dz. So what do we know? We know that dm equals density times dv, right? Is that correct? Okay. What is density equal to? Is there any way to express density here as a function of z or dz?
200Z.
Okay, 200z. So the dm will be equal to 200z times dv. And then how can we express our volume as a function of dc? What's the volume of this element?
It is pi r
Pi r squared.
times dz.
Okay, pi r squared times dc, right? So pi, radius, I'm not going to write it down yet, squared times dc. And what's the radius of that plate? Regardless of where I place my plate, what's the radius going to be? 0.5, always, right? That doesn't change. In the previous problem, our radius changed, right? So we had to express our radius as some variable, I think y. But here, our radius is always going to be 0.5. So I always include it as 0.5. So I express my differential mass as a function of z, right? dm equals rho dv, rho equals 200z, dv equals pi 0.5 squared dc. So I get that my differential mass dm is equal to, how much is 0.5 squared? That's 0.25, right? Okay, so 0.25, that's a fourth of 200, that's 50, right? So we get 50 times pi times z dc. Could somebody just make sure that this number is correct before I embarrass myself?
Yep.
Yes, I'm embarrassing myself, or yes, it's correct?
Oh. Yeah, it's a 50.
Huh. They don't make students like they used to, but it's okay. And the fourth and final step is to what?
Integration.
There's got to be some way to subliminally force kids to enjoy math so that when they get to college, they're like, oh, all excited about it. I don't know how. So let's integrate. We know that my x coordinate of the centroid, x bar, is equal to the integral of x squiggly dm. I said centroid, I meant center of mass, over dm. X squiggly equals 0. Thank you, Jenny. So x bar equals 0. We can say the same thing for a y coordinate. Y coordinate equals integral y squiggly dm over integral dm, but y squiggly equals 0. Therefore, this coordinate equals 0. So that doesn't change. Those are the values we were expecting. But now let's look at our z coordinate. Z coordinate equals integral of z squiggly dm over integral dm. Here we know that z squiggly equals z, so I'll just write down z. And dm from step number 3, and we know that it's equal to 50 pi z dz. What are my limits of integration for here?
0 to 1.
0 to 1, good. And we integrate. Let's see, we can take out the constants. So I'm going to take out 50 pi. And I get the integral from 0 to 1 of z squared dz. I take out my constants, 50 pi integral from 0 to 1 of z dc. 50 pi cancels out. Integral of z squared is 1 over 3 z cubed, 0 to 1. Integral of z is 1 over 2 z squared, 0 to 1. This gives me 2 over 3, or point, I'll just do 3 sig figs, so 0.667. Can somebody confirm this number?
Yeah.
Nice. So, any questions?
Yeah, I do have a question.
Okay.
For this one.
Mm-hmm.
It's more conceptual, I think.
Mm-hmm.
Seeing that the density is linearly goes up, could we have solved this by thinking about it as a cone? Like one of those snow cones or whatever?
I mean,
Shaped ice?
if you're trying to visualize its density, right, as if you're trying to visualize this as a homogeneous element, then yes, you could see this as a cone and then get the same answer.
Okay,
Okay.
yes.
I don't recommend it because this problem gives us an easy variation of density, which is just a function of z. When it becomes more complicated, it starts to become harder to visualize.
Okay.
And at that point, you want to kind of like just let the math do its job.
Okay.
Okay? Any other questions? These are good questions. It's actually a great question. But any other questions? Okay? Whew. There's a lot of work. It's a lot of material. But you will think, well, you won't thank me, but you will be happy that you did this when you get to your future classes and you realize that finding centroids is a given, right? People should already know how to do it.